Okay, thank you, Zenwa, for the great introduction. And then thank you so much for giving me a chance to introduce my research work at through this ICCEPM seminar. Today, the topic I'd like to talk is intuitive interface for seamless human-robot collaboration in construction. This is my brief introduction, but seems like Zenwa made a great introduction already, so I will just skip it. Yeah. So it's becoming clear that construction robots are rapidly emerging as a trend in the construction industry. So implementation of construction robots has surged recently, and it is expected to continue to grow in the future. On this slide, you can see some examples of construction robots, such as four-legged robots for surveying and mapping, and drilling robots, and rebar tying robots, and indoor finishing robots, and autonomous excavators, and bricklaying robots. These robots are now quite mature and then ready for the deployment in field. And then they are expected to bring a revolutionary change in the construction industry, as they can perform construction tasks with a high accuracy, efficiency, and safety. The potential of these robots to automate the construction industry is significant, but there are still several barriers that hinder the adoption of these robots. One of the major challenges is that the discrepancy between the as-planned model and as-built environment in construction site. Because most of the robots, they are pre-programmed and based on the planned BIM models. So such a discrepancy between the as-planned and as-built could lead to the errors and discrepancy in terms of the quality of their work. Also, construction tasks are often non-repetitive and have a long planning horizon, and this can make it particularly difficult to program the robots for these tasks. This is not only the problem of the construction robots, this is a general problem of entire robotics, that the field of the robots are, a lot of the robotic scientists are currently trying to tackle. Lack of compatibility between the current construction methods and robotic technologies is also a challenge. This can lead to delays and increase the cost when trying to integrate robotics into construction projects. And then lastly, there are some variation and differences in terms of the viewing the potential of the robots depending on who they are. So I mentioned here that as various perceptions of robotizations from different construction stakeholders, which means that some stakeholders are being hesitant to adopt robotics because of some concerns regarding the job loss or safety issues. And such concerns would lead to the resistance to change and also lead to the slow adoptions of the robotics in the industry. So in today's talk, before jumping into the main topic, I would like to quickly introduce one of our previous research that investigate such various viewpoints of the construction stakeholders regarding the adoption of the construction robotics. The questions in this study we tried to answer was how contextual factors related to job positions and work conditions influence the way people perceive and expect construction robots. So in short, we wanted to know that depending on the job task and depending on their levels within the organization, whether they prefer working with the robots or they are hesitant to working with the robots, or in terms of the level of the robot autonomy, how they prefer, and then what job characteristics impact their perceptions. To address these questions, we interviewed 36 construction professionals from various job positions. It includes the high level or low level construction managers and superintendents, and then the site workers from different trades. We divided those different trades into two. What is the structure or task group, and then architecture finishing groups. Then we asked them about their perceptions and preference regarding construction robots in a series of open-ended questions. Then we investigate how the factors such as the organizational positions or the dexterity or complexity of their work influenced their views on the adoptions of construction robots. This figure is a summary of our result. We analyzed how different stakeholders groups preferred the desired role and the autonomy levels of the robots in constructions. So there are several other very interesting findings, but regarding today's talk, I would like to just focus on the findings from we observed in the site workers. There's two groups, structural groups and then architecture finishing groups, and then we found that the majority of the respondents from the structural groups, they preferred using the assistive robots. So which means that they just they believe that the robots cannot replace their tasks, but they believe that the robots can assist their work because they believe that there are so much unpredictable uncertainty in their tasks, and robots cannot handle that. Okay, so which means that in structural task, we have to rely on the humans, still rely on the humans to handle out of scenario situations. On the other hand, the respondents from the architecture finishing groups prefer to control the robots by themselves, like the teleoperations or some control pad, because they believe that their job requires some expertise to fine-tuning the tasks. And then they are saying that in most of cases, their task does not follow a strict sequence of the operations. So the key point here is that based on our interviews, those are the site workers who are expected to work with the robots in the future. They believe that the robots cannot completely replace them. They believe that even though the robots are adopted, robots still need some human skills to fine-tuning the task and to address some of the out-of-scenario situations, which means that there is a need in terms of in-situ improvisations when we are designing human-robot collaborations. So in situ improvisation means that although the robots are performing the task based on the programmed or certain instructions, but whenever the robots should accommodate the in situ instructions of the workers to handle those out of scenario situations. These are the currently used interfaces to control the construction robots now. The important thing is that when it comes to delivering such improvisations I mentioned in the previous slide, these interfaces still have some limitations. The first interface is offline programming or pre-programming, which has been used in operations such as welding or assembly. So basically, they are in these interfaces, the operators are giving the instructions and then giving the pre-instructions. Then the robots will just follow the instructions sequentially. The problem is that these methods struggles to express the real-time information in construction site. So, which means that it cannot address such in situ variations. The other the interface is the teleoperation, which is also commonly used. The issue is that in order to use teleoperation, it requires the significant training for the human operators. And also, it would face some challenges in delivering in situ improvisation because of such a difficulty in controlling. Recently, a concept of the programming by demonstration has emerged. So it enables the robots to learn the movements performed by the human operators to perform under varying conditions and then to generalize them in the new scenarios. And so generally, they learn from how the human workers are performing, and then they are trying to generalize and then apply that rule into the other scenarios. However, it is still limited in imitating the demonstrated trajectories, and most of the works related to this method is still a little bit premature and in experimental stages. So to summarize, these are the commonly used interfaces. They do have some advantages, but they also have a limitation in terms of delivering in situ improvisations. So we wanted to address this challenge by exploring some alternative methods to deliver some in situ improvisations. One method we looked into was the use of the didactic gesture. So didactic gesture is using our hands to pointing the objects or pointing the certain location related to the tasks. This didactic gesture have been widely researched in the construction, in the general robotics field as one of the communication channels over the past decade. Didactic gesture can be an efficient and convenient way to convey specific intentions, especially in scenarios where verbal communication may be challenging. Humans also use didactic pointing to show the directions or objects all the time. And these types of the gesture can be used to control robots, making the interaction feel more natural. So the current limitation is that such a research in using the didactic gesture to control the robots are only investigated in the general robotics domains. And so their domain was their application was greatly different with the construction applications. As you see in this video, that most of research is more on the there are several objects on the table, and then the humans are pointing one of those objects. So the scale was small, and then dimension was only 2-dimensional. So our question was that whether if we are using didactic gestures in construction, how accurately it will be. So construction environment is 3-dimensional, and then the scale is very large. So the accuracy may degrade because of such a construction environment characteristics. In construction sites, the human workers are naturally using such a didactic pointing gestures. For example, it is common to point a specific location or object to indicate where something needs to be moved or installed or something like that. So in this study, we took a closer look at the accuracy of the didactic gesture in communicating special information in construction sites to investigate the feasibility of the didactic gestures. In particular, we wanted to see how special characteristics of the construction environment impact the performance of the spatial referencing when we use didactic gestures. To achieve this research objective, we did some experiment. We developed some special communication tasks that the human subjects use the didactic gestures to point one of the panels among the multiple panels on the ceilings and then the walls. So our goal was to see how accurately robots could understand such a human subjects, the gestures, in terms of which panel that the human subject is indicating. Now, we also wanted to compare how well humans and robots performed in these tests. So we would like to compare how human observed perceive that the pointing gesture of the human subjects compared to robot observers. This way, we could see that how well both the robot and human observers were able to interpret special information which is conveyed through the human gestures in different conditions. To understand the pointing gestures of the human subjects, we use the vision-based techniques, which is called open pose, to estimate the humans' skeletons of the human subjects, human pointers. I will mention as human pointers here. Suppose the robot is positioned facing the human pointers, then the RGB and depth images are collected simultaneously. In this case, that we get the third human pose from the RGBD images to identify the location of where the target in the environment. From there, we calculated the target position on the surface of the environment and finding the intersections between the gesture ray vector and the plane within that environment. Then we chose the panel that had the shortest distance to the target positions. First, we looked the accuracy of the directed gestures is affected by the different spatial conditions. Here we manipulated the target plane, which is a ceiling panels and wall panels, and the distance between the panel and targets. We found that the distance error on average was 1.1 meter for ceiling panels, while 0.4 meters for wall panels. We also found that the F1 score for wall panel was much lower than compared to ceiling panels. So in general, the pointing gesture was more accurately understood by the robots when we pointing the wall panels compared to ceiling panels. And also we discovered that the average distance errors of the side panels were significantly higher than the center panels for both ceiling and wall panels. These plots visualize the estimated points on the panels and the F1 scores for different distances between human and the targets. Here we found that the accuracy was better for panels that were closer to the pointer, with a good estimates obtained when the distance was 1 or 2 meters. But it became more difficult to estimate the location when the distance was 3 meters. This was also reflected in the recognition accuracy, which was dropped from the 90% at the 1 meter and only 40% at the 3 meters. The interesting point here is that the human observers were less vulnerable by the distance between the pointer and the targets. Next, we manipulated the location of the observers by changing the distance between the observers and the pointer and angles from the pointer. It's interesting to note that the average recognition accuracy was almost the same for both humans and robots, with a 56.7% for humans, 56.9% for robots. However, there are significant difference in terms of their standard deviations. Specifically, the robots' accuracy was higher when the observers are positioned in 2 or 3 meters from the pointers compared to human observers. However, when the distance becomes 4 meters, we see that robots' performance was greatly dropped, while human performance was maintained. So, to summarize the result of these findings, this experiment, we found that using the directed gesture in the large scale environment like a construction environment may have some significant challenges for both humans and robots, but humans are more vulnerable because of the scale of the environment. Humans' accuracy in interpreting the robot's accuracy in interpreting the human's directed gesture was greatly affected by where that target is, and then how far that target is, and how far the robot is positioned from the humans. So this study is throughout this experiment, we found that in order to use the didactic gestures, we need to provide some visual feedbacks for humans and at the same time for the robots to understand where the human is pointing. So we explored that what is the effective visual feedback method that could enhance the accuracy of using didactic gesture to delivering the special information to the construction robots. Our approach was to use the laser pointers. Using laser pointers as a visual indicator. So for the human instructor, they can clearly see that where they are pointing, and also the robot observers can better understand where the human pointer is pointing. The reason why we chose the laser pointer is that they are currently commonly used in the construction sites for various purposes, right? As you see in these images. So laser pointers could produce the coherent beams of the light, so they can focus in a straight line with a very little divergence onto a small area. Okay? So we combined this laser pointing with our didactic gesture-based interface. This slide shows the workflow of our proposed didactic gesture-based interface. Before receiving the task specification from the human operators, the robots are explores its surrounding environment to build the global 3D maps. Then the target location is estimated only based on the human operated didactic gesture. At this stage, robots doesn't care about the laser pointing. So based on the human operators, the hand gestures, robots are approximate where they are pointing. Then robots starting to move to the areas, and then those target location will be further fine-tuned using the laser pointing techniques. During this process, once the target location is determined from the gesture or laser pointer, the robotic system simultaneously performs some motion plannings and execute the planned motions. This video shows an example of delivering in situ work instruction to a construction robot using our interface. In this trial, the human operator is pointing to the 4 points on the ceiling drywall to make the rectangular shaped opening for an air vent. We evaluated our interface through the experiment involving 6 participants. We wanted to compare our methods with the teleoperation methods. So we asked the subjects to do 2 task trials. One is using our interface, which means the laser pointer and their didactic gesture. The other one is that joystick interface, which is the common method, like very similar to the teleoperations of the robots. And then these figures shows the distance errors, and then task completion times, and then system usability of these 2 methods. Then we see that our proposed interface is accurately estimate the task location and complete the tasks quite efficiently, and also the system usability rating is also acceptable even compared to those teleoperations. And then so overall, I mean, as you see that although we can see some of the trend here, but statistically, there was no difference between these two methods. So overall, our experiment shows that our interface is as effective and efficient as the traditional joystick interface, which represent the teleoperations. Also, this graph shows that how effectively laser pointing can enhance the accuracy in terms of the didactic gestures. If we are compare with the experiment from the previous study, which used only didactic gesture, when we use a didactic gesture and laser pointing, the distance errors was greatly reduced. So those part is more about the task accuracy and the task performance. We also evaluated how subjects feel comfortable in using our interface. We used the NASA Task Load Index questionnaires. We evaluated the cognitive load when subjects use our interface compared to conventional joystick interfaces. As you see here is that averagely our interface demonstrate the better scores in terms of the mental demand and physical demand and efforts, which means that when subjects use their own gestures and then the laser pointer, they had the less mental demand. They feel the less mental demand and physical demand. So summarize, our interface reduced the mental demand up to 77%, and then efforts level up to 49% compared to joystick interface. So to summarize, so we found that with our interface, with those didactic gesture and laser pointing, subjects were able to complete the tasks with high accuracy and efficiency. Then through this post-experimental survey, we found that they reported lower mental demand and effort levels compared to the joystick interface. These results highlights that when it comes to the delivering in situ task instructions, using such a didactic gesture and the laser pointer could be a viable alternative to the conventional or handheld controller interfaces, which is currently used in the construction robots. Lastly, I would like to talk about the remaining challenges and future research directions. The left side graph shows that the current research, the research in the subject matter of the human-robot collaboration in construction. As you see, majority of the studies took place in the laboratories or controlled environment. There are fewer studies conducted directly on construction sites. So this highlights one of the major hurdles in the field of the HRC in construction would be the difficulty in transferring laboratory tested prototypes to practical applications. Another major concern is the lack of the dependability principles in the noisy and unstructured conditions of a construction site. This can greatly impact their operability and performance. Without robust operation algorithms, the robot's efficiency can vary greatly, leading to unpredictable behaviors and decreased performance. Also, there is a need for some new training program to help workers learn and adapt to these emerging human-robot interfaces. Regarding the human-robot interfaces, I believe that the extended reality, XR, could be one of the great alternatives. This figure shows the overview of the system architecture and the key components that constitute the XR application for human-robot interactions. In this architecture, a set of the sensors collect the information from the humans and the real-world environment. These sensors could include the RGB and 3D cameras and game and VR controllers and touch inputs and wearable devices. Data are sent from the physical system to the virtual system, from virtual system to the physical system using communication mechanisms. Interaction tools are used to process the data obtained from the sensors, and the robot control tools are used to manipulate the real-world environment based on such inputs. When it comes to construction domain, XR has been successful as an interface for skilled workers to utilize robots for technical craft skills such as plastering, carpentering, and so on. The left video shows the AR-based interface developed by a research team at the ETH Swiss, which is called the Interactive Robotic Plastering. This system allows designers and skilled workers engage intuitively with an in-situ robotic plastering process by projecting human intentions through the AR interface, converting them into motions. There are several future research directions for developing human-robot interfaces in construction. One important aspect that we should consider is ensuring transferability of the interface across the various tasks and scenarios. The left table shows the list of the basic construction tasks and the common information required for each task. As we can see, position and orientation information is commonly needed data in most of these tasks. So regarding our didactic gesture-based interface, while it can accurately estimate the 3D task positions, future interfaces should be adaptable to handle complex task instructions, not only for the specific location, also for more about the areas or reasons or objects to be handled by robots. And here, we could focus more on incorporating XR-based support to construction HRC to enable natural and two-way communication between the workers and robots. This will be the end of my presentation. I would like to wrap up with an acknowledgement. I would like to acknowledge the financial support from the Seoul National University for this study. And also, I would like to acknowledge the great contribution of my PhD students, Sungbu Yoon, who is the current PhD student at Seoul National University, and Yesil Kim, who is my former PhD student and currently at Georgia Tech. Thank you so much for your attention.